Okay, this is a snapshot on general probability problems. Once again, you should be somewhat familiar with probability and a little bit about counting concepts before attempting this worksheet. So again, either you've looked over the book, my lecture notes, etc. All right, so you should stop the video, try to answer the following questions, and then start the video and check to see if you got them right. Okay, so again, stop, work, play. All right, the probability of an event is always between what? Which two numbers? Between 0 and 1. That's just by the nature of the definition of probability. It's always between 0 and 1. Second one, if an event A cannot occur, then the probability of that event is 0 because it can't occur. If an event A is certain to occur, then the probability of that event is 1. Suppose there's a 60% chance of rain today. Then there is a 40% chance that it will not rain. The events rain and no rain are what is referred to as complements. They are complements. That is opposite. Exactly one of them or the other one will occur, right? It's either going to rain or it's not going to rain. When two events are opposites, like we're saying here, they're referred to as complements. And again, I'll just refer you to the notation for a complement. The complement of A is denoted by, just gave you that, and consists of the outcomes that are not part of A, right? That are not in event A. Now, oftentimes an event is described. So typically you describe the complement. Now we're going to move on. So again, stop the video and work problem. Well, we didn't really move that far, did we? Okay, an event and its complement, that should be, all right, probabilities are related by what equation? So how do you relate the probability of an event and its complement? The probability of an event plus the probability of the complement has to equal 1 because exactly one of them will occur. If two events cannot happen at the same time, we say they cannot happen at the same time. They are mutually exclusive. Moving on, the probability that is computed with the knowledge of additional information. The knowledge of additional information is called a conditional probability. Conditional probability, okay? Probably taking me longer to write this down than anything here. And it is denoted by the probability of event B given event A has occurred. So this vertical line here indicates the event on the right hand side or the additional information on the right hand side has happened. The sample space may change, but the methodology or the way we calculate probability does not change, okay? So the way we calculate probability, should have gave myself some additional room here, huh? Probability does not change, all right? And that's the idea behind a conditional probability. There's nothing special about it. The only thing is you're given additional information, but you always are making decisions or whatever you do. You always base it upon what you know, right? If you know it's going to rain, you're going to take the umbrella, right? For any two events A and B, we have two important formulas, right? So we have two events A and B, two very important formulas. The probability of A or B is the probability of the first one plus the probability of the second one minus the probability that both of them occur. The probability of A and B happening is the probability of the first one times the probability of the second one given the first one. Now, whenever you encounter a probability problem that involves or the word and, you should seriously consider writing these two formulas down. Notice this formula here, and, involves the conditional probability. So oftentimes when you're given a probability problem and you're being asked to find this, oftentimes this formula can come in handy, all right? All right, moving on. Two events are if the occurrence of one does not affect the probability the other one occurs. Two events are independent. They're independent means they have no influence on the other one. If two events are not independent, we say they are, well, dependent. Okay? So, independence means they have no effect on one another. Mutually exclusive means, I might as well do that, huh? Add some color to this thing, huh? Mutually exclusive means they can't occur at the same time. Whereas independent, they don't influence one another. There are special things we know about those two situations, but again, these two formulas, if the information is available, will work all the time. Now we're going to get into some probability problems. So again, I hope you stop the video and you try working out the problem. And then start the video up and check your answer, okay? Now, I'm not necessarily going to reduce things to lowest terms or convert it to a decimal or convert it to a percentage, okay? I'm going to probably just leave it as a fraction. We have a survey of 10,000 families in a certain town, and they're categorized as follows. They either own a home, a condo, rent a house, or they rent an apartment. A poster samples a single family from this population. Assume a family owns exactly one of the above categories, so there's no overlapping. That's important. What is the probability that the sampled family rents a house? This is the fundamental definition of probability. If you can count how many ways you can choose a family that rents a house, then write it down. If you can determine all the possible families that can be selected, we can. That's the denominator. This fraction represents the probability that a sampled family rents a house. The numerator is how many ways the event can occur. The denominator is the sample space. What is the probability that the sample family owns a condo or they rent a house? There's a probability question with a keyword in it, or. Now, I told you earlier that you should consider using the formula whenever you encounter the word or and. But the thing is, I can easily count my way through this problem. I know how many ways I can pick a family that owns a condo or rents a house. 1,478 plus 912. These two do not overlap because a family owns exactly one of the above. In other words, the probability a family owns a condo and rents a house is 0. So again, we really didn't need the formula, but it works. The denominator is the sample space, 10,000 families. Do you do the math? That is your answer. Okay, moving on. Example number 2. Stop the video. That's why I try to pause talking for a second in order to allow you to give you time to stop the video. All right, the Centers for Disease Control reports that in the year 2000, there are 2,057,979 boys and 1,963,747 girls born in the United States. We want to approximate the probability that a randomly selected newborn baby is a boy. They want it to 2 decimal places, okay? Well, I'm not going to do that. Again, you know how to do that. This is not an algebra course. All right, I want the probability a newborn baby is a boy. How many ways can I select a newborn baby boy? 2,057,979 ways. What is the sample space? The sample space is the sum of these two numbers. So simply add these two numbers up, put that in your denominator, you do the math, and round to 2 decimal places, okay? I'm going to move on. We're already 11 minutes into the video here. Moving on, stop the video, work the problem, all right? Okay, we have a table based on a survey of voters in regards to a tax proposal. Now, I've discussed this in class. Hopefully you're familiar with the table, but I'm going to work the problems and I'll try to explain things as I go, but you should try it first, right? So here's the information. I'll just point out that our sample space is 370 people. We're going to choose somebody at random, and we want the probability that a randomly selected person is likely to vote or favors the proposal. Let's see, I think this is likely to vote or favors the proposal. Now this is an or. So the probability that you are likely to vote or favors the proposal is the probability you're likely to vote. Sorry, still have to get used to this. Plus the probability you favor the proposal minus the probability that you vote and favor the proposal. Okay, gotta get used to my pen here. All right, so that is the OR formula, right? Again, you might not necessarily need this for this problem if you know what you're doing, but here it is. The probability that they vote, well, there's 240 that vote out of 370. The probability they favor, the number that favors 150 out of 370 minus they vote and they favor. So you're likely to vote and you favor is 100. So 100 out of 370. Notice we were not given any information here. So for each one, the sample space consisted of 370 people. So you do the math, add your numerators up, divide by your denominator, which is 370, and you'll have your answer. Part B, find the probability a randomly selected person is likely to vote given they favor the proposal. So now we know they favor the proposal. So we have a conditional probability here. The probability that they vote if we know they favor the proposal. Well, if we know they favor the proposal, this is our sample space now. In this sample space, there are 100 people that are likely to vote. 100 that are likely to vote. So, all right, there is a total of 150 people in this sample space. So, once again, here's a key word here. When you see this word given, you are talking about a conditional probability. You need to ask yourself, how is the sample space affected by the given information? They favor the proposal. The number of people that are likely to vote in this world is 100. The number of people in this world is 150. The next problem. Find the probability a randomly selected person is likely to vote and they favor the proposal. So we want the probability they vote and favor. In this problem here, we are no longer worried about pop-up messages, right? All right, vote and favor. Notice we do not know any additional information. How many people in this survey vote and are in favor? So that you're likely to vote and you're in favor, 100. How many people are in the survey? 370. So 100 over 370, we actually did this above here, but I wanted to point out 3 different problems. Okay, 3 different ones. Really the difference here that I want to emphasize is between B and C. In B, we are told they favor the proposal. So we change our sample space. In the third one here, we're asking, do they favor the proposal at the same time they are likely to vote? There is no additional information provided in this one. Moving on. Okay, look at the problem, stop the video, give it a try. All right. Among those who apply for a particular job, the probability of being granted an interview is 0.1. So the probability you get an interview is 0.1. Among those interviewed, the probability of being offered a job is 0.25. You might not realize this, but this is given information. You know they've been interviewed. The probability of being offered a job is 0.25. We want the probability an applicant is offered a job. So the probability an applicant is offered a job is really, they have to be offered the job along with the interview, right? Interview and they get the job, right? That's really what you mean by the probability of a job. Some problems are not all that clear. Just the way it is. But if you think about it, the probability you get a job, you have to get an interview and you got to get the job. Well, we know for and, there's a formula. That formula for this particular problem is the probability of the first one times the probability of the second one. Sorry, let's see, let me fix that. Given the first one, well, the probability of an interview we have right here, 0.1. The probability of a job given an interview, I want to say interval. Don't know why. 25. When you multiply this together, you get 0.025. So that's the probability you're going to get the job. It's about 2.5%. Moving on. Number 5. Oh, let's see. I'm going to have to hold off on number 5. I didn't give us enough space here. So let me work the next example. I really need to fix that because this is going to take a little space here to solve this particular problem. But anyway, so let's move on down to the bag that contains the following number of discs. So we have a bag. We have 8 discs. Some of them are shaded and some of them are not. If they're shaded, we say it's gray, okay? All right. One disc is selected. We want the probability that we select a 3 given we have a gray disc. So this is a conditional probability. We're told we have a gray disc. So we know we're only looking at the gray disc. There are 5 gray discs. How many of them have a 3 on it? 1. So 1/5. Next one. The probability of an even given a white was selected. So now we know a white disc was selected. Our sample space consists of 3 discs. We want an even number. Of the 3 white discs, there's only one even number, so 1/3. The probability of selecting a gray, given the number was selected the probability of selecting a gray given the number selected was at least 5. So we know the number selected was at least a 5, so we're talking about 5, 6, 7, or 8. So there are 4 discs. Of those 4 discs, 3 of them are gray. So this is the basic definition of a conditional probability. The given information is changing the sample space, right? For the first one, we focused only on the 5 gray discs. For the second one, the 3 white ones. For the fourth one, the disc with a number that was at least a 5. 4 of them. Moving on. What's the probability the disc is gray and the number is at least a 4? We are not given any additional information here, so our sample space consists of 8 discs. How many discs are gray and the number is at least a 4? 1, 2, 3, 4. So 4 out of 8. Moving on. Are the events A equal to select a gray and B equal to select a number at least 4 independent? So do you think if I know I selected a gray, does it affect the probability I'll get a number that's at least a 4? Well, if I know I have a gray, there are 5 ways that can happen, right? How many of these things are at least a 4? 1, 2, 3, 4, right? 4/5. So that did change the probability of getting a number that's at least a 4, because at least a 4 is 5 over 8, right? At least a 4 is 5 over 8. 1, 2, 3, 4, 5, right? 5 out of 8. But if you know it was gray, that probability changed. So this one's being influenced, so they can't be independent of one another. You might have to rewind the video on that one, huh? The probability a disc is white or the number is odd. What's the probability the disc is white or the number is odd? Well, again, we have 8 discs. We need the disc to be white or odd. Well, white, white, odd. Let me use a different colored marker here. White, white, odd, 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 white, odd. That's it. They're white or odd, right? So 1, 2, 3, 4, 5. So there are 5 discs that are white are odd. There are 8 discs in total. We were able to count our way through probability here, so we really didn't need the OR formula, which is very kind of, again, restricted in the type of problems we can really give you there. All right. Now, 2 discs are selected with replacement. What's the probability that a gray is selected first and a white is selected second? So I need the probability I get a gray first and a white second. Well, that's an and probability, so I need the probability I get a gray first times the probability of a white second given a gray first. Well, the probability of getting a gray first is going to be 1, 2, 3, 4, 5, 5 out of 8, right? The second one's a conditional probability. I told you I got a gray one first, but I put the disc back. So there are still 8 discs. Of those 8 discs, 3 of them are white. So 15 over 64. Now we're going to assume that we do not put the disc back. So we're asking the same question here, but we do not put the disc back. So once again, our formula is going to be the probability of a gray first times the probability of a white second given gray first. Well, probability of a gray first, 5 out of 8. Now, we did not put the disc back. So we now have 7 discs because one of these gray discs are gone, right? But there are still 3 white discs. So 3 out of 7, 15 over 56. So again, I hope this video helped out a bit. You can rewind it, play it over again, and if there are any particular issues, just let me know, and I'll try to fix them. Oh, yeah, I'll work this one. That's an issue, huh? All right. Committee of 5 people is to be selected from 4 teachers and 7 students. What's the probability the committee selected will have 3 teachers and 2 students on it? All right. Basically, this is what's going to happen here. The first thing you need to know, what is the possibility of forming a committee of just 5 people? Well, the number of ways you can select a committee of 5 people, and you don't care if they're a teacher or a student, just 5 people, is a combination of 5 people selected from 11. That's the denominator here because that's the number of ways anything can happen. The number of ways you can choose 5 people from 11 because we're not making a distinction between teachers and students, okay? Now, for the numerator, which is the number of ways we can choose 3 teachers and 2 students, well, the number of ways we can pick 3 teachers, we need to pick the 3 teachers from 4. That's a combination. We also need to pick 2 students from the 7 students. That's a combination. We multiply them together. It's a combination because we do not have any order. When you pick, you're on the committee. Nothing is being said differently as you get picked. You're on the committee, you're on the committee, you're on the committee. So, the numerator is simply the number of ways we can pick 3 teachers from 4 times the number of ways we can pick 2 students from 7, and then we divide that by the number of ways we can just pick 5 people in general from 11. I'm going to work this one out in class for you, but I'm going to give you the answer. So if you did this the long way or my way, you have the answer. So let me get the numbers for you. Okay, so here are the numbers. 4 times 21 divided by 462. So you can take a look at that. I'm going to actually work this one out in class with you because this is always on the final exam. Questions like this. All right. That's it, I believe.